Dear friends, hearty welcome to the online problem solving session series organized by Maths Aspirants groups. As you know, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India, started by myself in 2017, and we used to organize several online programs to help the students who are preparing for different national level competitive examinations. As a part of that problem solving session series, today we blessed to have Miss Dipali A. Savant, Assistant Professor, 𝐾𝐤𝐸 College, Matunga, Mumbai, with us to handle a session on permutations and combinations. This is a topic newly introduced to IIT JAM syllabus this year. It was there in some previous years, but recently this topic was not there. And now, this time IIT Bombay is conducting the JAM examination. So this topic is newly introduced. So we are organizing this session mainly focusing on IIT JAM examination. So I'm sure that this session will be really helpful in your preparations. I would like to express my sincere gratitude and thanks to Ms. Dipali for accepting our invitation and joining with us. I welcome everyone to this program. Welcome, Dipali.
Thank you, sir. I'm really glad to have myself over here. I'm very happy that IIT Bombay took an initiative to do justice to combinatorics. It is one of the very easy and kind of very interesting topic. Though it is not my area of expertise, but we'll start with the session. Just give me a moment. Yeah, the topic what is stated in the syllabus actually includes permutation, combination, and binomial principle. I will be taking up to binomial principle today, but there are some more topics which I think should be included, or you may have questions based on that in your upcoming examination. So I will just brief you about them and go ahead. In order to understand permutation combination, one has to be thorough with four counting principle. There are four basic counting principle: addition principle, multiplication, subtraction. Basically, talks about finding the cardinality of a complementary set, and division principle, which is mainly about partition. So though it is very, very basic, I request you all to pay attention, because this will, with the help of this only, I will be discussing my problems ahead. So going ahead with the addition principle. Okay. So coming to the addition principle, suppose this is an all-empty set. I'm not referring to any particular subset of R or something. Suppose S is an all-empty set, which is expressed as a union of SIs. There are M SIs, and such that all these SIs are mutually disjoint. That means if I take the intersection of two different SIs, then it is empty. Then my S, the cardinality of S, size of S, cardinality of S, or number of elements in S. Okay, these are all going to be treated as a synonyms over here. So cardinality of S will be summation of cardinalities of SI. So it's a very straightforward principle. Like you take S. So suppose if I have to show you in the form of a diagram. Okay, let me not get into it. I'm not able to figure out the thing over here. So suppose I'm taking a set S and I divide it into M parts, and the total number of elements in S is total number of summation of total number of elements in SI. Let us understand this through an example. So suppose a university student wish to take mathematics course or a biology course, but not both. So he can either opt for maths or biology. Suppose he has 4 mathematical courses and 3 biology courses. Then the question is, how many choices he has? So since he is not going to opt for both the courses at a time, the total number of choices the student will have will be 4 plus 3, that is 7 here. Okay, because he has 4 choices of mathematics. So let me say my S1 is the number of choices in mathematics, my S2 is the number of choices in biology. And since he is not planning to opt for both, okay, total number of choices by addition principle will be 4 plus 3, that is 7. Coming to the multiplication principle comes into picture when your a set has the ordered pair or n tuple. So for example, as a definition, suppose my set S is a set of ordered pair A comma B, where the element A is coming from the set S1 and the element B is coming from the set S2, right? There the cardinality of S1 is P and the cardinality of S2 is Q. Then in that case, the cardinality of S is going to be P cross Q. Now this is something which we all must have used when we studied vector spaces. So if you actually try to calculate the dimension, I don't know, but I think in that particular way, suppose you're talking about dimension of Rn, it turns out to be, it is actually n. Let me not get into this particular part. So what it says is if your S is a cross product of two finite sets, then the cardinality of S is the product of the cardinalities of two sets S1 and S2. Now, this is a good example what we get in Bruvaldi. The reference book for this particular paper is Richard Bruvaldi, Introductory Combinatorics. I will show you the book towards the end of my session. It's a very simple book for an undergraduate student. So, Introductory Combinatorics by Richard Bruvaldi. From there, I have taken all my examples. So, a chalk comes in 3 different lengths, 8 different colors, and 4 different diameters. Okay, then how many different kinds of chalks are possible? So now if I'm talking about one particular chalk, one particular type of chalk, then I will have to select, is it okay if I answer all my queries towards the end? I'm already in the full screen mode. So if possible, let me answer all my query after the end of my session. Please write down your, let me finish my session and answer the query. Okay. So if I have to select one chalk, I will have to finalize the length, I will have to finalize the color, and I will have to finalize the diameter. So suppose I consider S is a different set of all the different kind of chalk. Now one particular chalk is decided by its length, a color, and a diameter. Now for where the L comes from the set S1, that is a set of length, color comes from set S2, and diameter comes from the color, set S. So S1 is a set of choices for the length, and we know that as it is mentioned in the problem, the cardinality of S1 is 3. S2 is a choice of diameters, and the cardinality of S2 is 8. S3 is the different choices available for the for the diameter. The choices is 4. For color, it is 8. So then, if I have to find the cardinality of S, I will apply the multiplication principle. So by multiplication principle, cardinality of S will be equal to cardinality of S1 into cardinality of S2 into cardinality of S3, which is 90, 3 into 8 into 4, which is 96. Okay, so that is how I apply my multiplication principle in this particular question. Now here is another good example. Suppose my number alpha is expressed as 3 raised to 4 pi square into 11 raised to 7 into 13 raised to 8. The question is find out the number of positive integers which are factors of this number alpha. Okay. Now any factor of alpha will have the multiples of, it will have power of 3, a power of 5, a power of 11, a power of 13. Okay. So in general, any factor of alpha will be equal to 3 raised to I into 5 raised to j into 11 raised to k into 13 raised to f. That will be the format of any factor of alpha. Now, how many choices do I have for powers of I? The maximum power of I in how many options do I have for power of 3? The maximum power of 3 available in alpha is 4. So the value of I can range from 0 to 4. Okay. Similarly, our maximum value of j, which is a power of 5, it can go up to 2. So j will vary from 0 to 2 because alpha has only 5 square term. Similarly, if I look at k, the maximum value of k can go up to 7. So for k, I have the values, all the integer values starting from 0 to 7. And similarly for L, which is a power of 13, it can go maximum up to 8. So now let us count how many choices I have for I, j, k, l. So for I, starting from 0 to 4, I have 5 integer values. So for I, we have 5 choices. Similarly for J, which is running from 0 to 2, we have 3 choices. For K, which is running from 0 to 7, we have 8 choices. And for L, which is running from 0 to 8, we have 9 choices. Now, any combination of IJK will form one factor. Okay, so total number of choices, once again, I will use multiplication principle. I'm sorry, I have written theorem over here. I will correct it later. It is multiplication principle, which gives me my answer will be 3 into 5 into 3 into 8 into 9, that is 1080. These many factors I will have for alpha. Okay, so that is how I apply the multiplication principle in such kind of question. It comes into picture when you normally have when you are dealing with the cardinality of a set which contains n tuple. Coming to a subtraction principle comes into picture when you are talking about the cardinality of a complement of a set. So let A be a set and U be a larger set. So we have been taught from school or maybe from our 11th and 12th standard, the bigger set is known as the universal set. So U is my universal set containing A. Then A bar, which we also referred as A complement, it is set of all X in U such that X does not belong to A, right? Then in that case, cardinality of A bar, that is complement of A, is cardinality of a universal set minus the cardinality of A. Now let us see a good example which can be a part of your examination. So here is one example. Once again, it is from Ruvaldi. A computer password has to consist of 6 symbols, a string of 6 symbols, okay, which are taken from a digit 0 to 9 and the lower cases letter from A to Z. So how many computer passwords have repeated symbols? Okay, how many computer passwords will have? Okay, so let us understand how many symbols we have got. We have 10 digits and 26 alphabets. Okay, so in all we have 36 symbols which can be arranged to form a password. Right? So let us say U is the universal set, which is a password of 6 symbols. Right? Now for each place, now they never said like so for each place I have 36 symbols. So for the first place I have 36 choices. For the second place I have 36 choices, and similarly for the 6th place also I have 36 choices. Now as you can see here, my universal set, okay, it is basic element of a universal set is a 6 tuple. So I can apply my multiplication principle, and with the help of multiplication principle, the cardinality of U will be 36:6. Right? Now let me take A is a set of 6 symbols with the repeat set of 6 symbol password with the repeated symbol. Okay, so I can have one symbol repeating 2 times. I can have one symbol repeating 3 times, and so on. So repetition is allowed. The complement of this would be a set. So if I'm looking at E bar, the set of 6 symbols without any repetition, right? So if I take the first place, for the first place, I can choose any one symbol out of 36 symbols. So for the first place, I have 36 options. Once I selected one symbol over here, for the next place, I have 35 options. Once that is selected, for the next place, I have 34 options. Then for 33, then 32, then 31. Okay. So now I have the choices for first to 6th place. Once again, I apply my multiplication principle. And then the cardinality of A bar will turn out to be 36 into 35 into 34 into 33 into 32 into 31. Right? One can write it as 36 factorial divided by 30 factorial. I'm not rushing to that particular point. We can discuss that later. But I am not interested in cardinality of A bar. I'm interested in cardinality of A. So what I'm doing is I'm applying the subtraction principle. So A, which is the complement of A bar, by applying the subtraction principle, cardinality of A will be cardinality of U minus the cardinality of the complement of it, which turns out to be this huge number. Okay, how did I get it? Just put the value, simplify, you will have the answer. Now, once we are done with the subtraction principle, we'll go ahead with the division principle. Now, division principle basically deals with the number of partitions or the size of a partition. You can look at it as the way you want. I don't know how many of you are actually doing the introductory combinatorics, but we have very nice chapters in duality towards the end discussing the partition. Okay, but for exam point of view, I'm not going to talk that right now. So let S be a finite set, partitions into k parts. Right? You have a set S, you have divided that into k parts in such a way that each part contains the same number of objects. Right? So now, how many partitions you need? So then the value of k is cardinality of S divided by the number of objects in each part. Similarly, you can use this formula as, so if you know the number of objects in each part, you can find how many partitions you're going to get. Other way around, the number of objects in each part is cardinality of S divided by K. So how many partitions you need, depending on that, you can decide how many objects will be there in each part. Okay. So as an example over here, there are 740 pigeons in the collection of pigeonhole. Each pigeonhole contains 5 pigeons. So find the number of pigeonholes are required. So now you know the cardinality of S. Your set S is set of pigeons, which is 740. And you have already decided that the number of elements in each part is going to be 5. Now the question is how many partitions you need. So obviously the answer is 740 divided by 5, which is 140. Now here are some questions what one should try. So let's go ahead with this question. So how many odd numbers between 1000 to 999 have distinct digits? Okay. So let us understand this question here. So first of all, the point to be noted is I'm just going to take odd numbers here. That is one thing what we should note down. Okay. So any odd number between 1000 to 9999 is going to be a 4-digit number. Okay. So let us say D1 digit denotes the first digit, D2 denotes the second digit, D3 denotes the third digit, and D4 denotes the fourth digit. Right? The number of odd numbers with a distinct digit or my required answer will be the product of the choices which I have for D1 into D2 into D3 into D4. Okay, what I'm applying is a multiplication principle. Let us talk about D4 first, because in the question they have mentioned my number is going to be odd. Okay, for D1 to D4, I can fill these places by using the digits from 0 to 9. Okay, now since the question says I need an odd number here, the value of D4 has to be an odd digit, right? So the number will be odd if D4 will belong to 1, 3, 5, 7, and 9. So as I can see here, for D4, I have 5 choices. Okay. Now my number has to be a 4-digit number. Okay. So there is another condition on D1. So let us see what is the condition on D1. The condition on D1 is D1 has to be a non-zero number. Okay. And it has to be different from D4. So if D1 has to be non-zero, D1 will belong to a set 1 to 9. Okay. Plus it has to be, so first of all, for D1 from this set, it has 9 choices. Okay. And again, D1 has to be different from D4. D4, if you look at the set of D4, okay, let me just scroll down. So D4 is again a non-zero, sorry. One minute, just okay. Okay. So if you look at your D4, the set of D4 doesn't contain 0, right? And again, as I said, D1, which we are going to consider, D1 is again a non-zero number. So D1, for D1, we have 9 choices here, but one non-zero choice has already been taken by D1. So D1 is different from D4. So one more choice is gone. So therefore, for D1, we have only 8 choices. Okay. For D1, we have 8 choices. Now coming to D2. Now D2 and D3 both will belong to 0 to 9. But D2 has to be different from D1. So from 0 to 9, I have 10 choices. And since it has to be different from D1 and D4, the number of choices for D2 reduces to 8. Okay. Again, for D, we have 10 choices. But now D3 different from D2, D1, and so for D3, we have already lost 3 choices. So for D, we have only 7 choices. So by multiplication principle, okay, for D4, I have written it slightly different, but just try to ignore that part. So for D1, D4, I have 5 choices. For D1, I have 8 choices. I have 8 choices for D2, and I have 7 choices for D. So total number of 4-digit number required condition mentioned. That number has to be odd and all the digits have to be distinct. The answer turns out to 5 into 8 into 7. That turns out to be 240. In case this number is slightly different from whatever answer you are getting, we'll just discuss that after. Okay. Now here is the exercise question what I would like you to try when I will share my notes. These are the questions which you should try, and all these questions what I have given over here should follow with the help of the basic principle. The basic principle is addition, multiplication, subtraction, and division. You don't need any permutation and combination here. You can do them better with the help of permutation combination. But right now, we will not discuss that here. Oh, coming to a permutation, which is the topic of your examination. The term permutation can be treated as a synonym for arrangement. Okay. Now, when it comes to the arrangement, you can arrange the alphabets to form word. You can arrange the alphabets and the numbers to form a pair number plate. Again, it is a straight line arrangement for the photographs. You have n number of questions here. Okay. So first of all, let us understand now with the formula of permutation, what I see here. Okay. This is a formula what we see in context of these problems. Okay. Word formation, car number plate formation, straight line arrangement for the photograph. That is where you can arrange the permutation. Though I have not mentioned here the permutations of n symbol, that is Sn. Okay, is also a part of this that can be studied different. That should be included here. Right now, I'm not talking about it, but if you're talking about arrangement of n numbers, it's 1 to n among themselves, which gives you a group Sn. Okay, that can also be discussed here. Right? Going to a permutation, the formula for permutation, that means the arrangement of R objects out of n distinct objects. Okay, and this is a straight line arrangement. You are arranging them in a line. That is given by NPR, which stands for n factorial divided by n minus r factorial. So let us take this simple question. So suppose I have to form a 4-letter word. The number of 4-letter words that can be formed by using the alphabets A, B, C, D, E is at most. Now here I have 5 distinct alphabets. From this 5 distinct alphabets, I have to form a 4-letter word. Now forming a 4-letter word means what? I'm supposed to choose 4 alphabets from here and arrange them. Okay, so I have 5 distinct objects. I have to arrange 4 distinct objects out of these 5 objects, and it's a straight line arrangement. Why it is a straight line arrangement? I'm actually forming a word. Okay, so the number of arrangement over here is given by 5p4. By formula, it is 5 factorial divided by 5 minus 4. That is 1 factorial. That turns out to be 120. Okay, let us take another good question over here. How many 7-digit numbers are there such that the digits are distinct and taken from 1, 2, 3, and 9 such that the digit 5 and 6 do not appear consecutively? That means what I'm saying is you will not see, suppose if you are taking a 7-digit number, okay, you are taking a 7-digit number, then you will not see 5 and 6 together. That means you will not see a sequence 5, 6 in the number, okay, or neither you will see a sequence 6, 5 in the number. How to add a pen over here? It's not a problem of adding a pen. Anyway, let me not waste my time in that. Okay, so you will not see a sequence 5, 6, or you will not see a sequence 6, 5 in this particular number. Okay, so first of all, identify how many 7 digits number we can see here. So first of all, 7 digits number. So U denotes a 7-digit number which are formed by using a digits from 1 to 9, which are distinct. So I have 9 different objects and I'm taking 7 objects and arranging them. So the cardinality of U is going to be 9P7. Okay. Now S denotes the 7-digit numbers from U where 5 and 6 do not appear consecutively. Okay, that means we do not come across a number containing a sequence 5-6 or 6-5. There is no comma here. It is 6-5. You will not see 56 or 65 in your whatever number you are constructing. So let us take the complementary set of S. So suppose S bar denotes the 7-digit numbers where 5 and 6 appears consecutively. So you will either see a sequence 5-6 or you will see a sequence 6-5 in the number. So we'll work out first of all, we'll see how many cases we are getting for the sequence 5-6. That means the number which contains a sequence 5-6. So we'll work out the sequence 5-6 and then we'll have a similar argument for the sequence 6-5. Okay. So for now, if there is only one way of generating a number 56 in the 7-digit number. Your 5 can take first position. Okay. And 6 appears here, right? 6 appears here. So now if 5 is first and if 6 is appearing here, then for 5, how many options are? If I take 5 here, 6 can appear here. If I take 5 here, 6 can appear here. Okay. So if 5 takes the first place, 6 can appear in the second place. If 5 takes the second place, 6 can appear in the third place. If 5 takes the third place, 6 can appear in the fourth place. If 5 appears in the fourth place, 6 can appear in the fifth place. If 5 take the fifth place, 6 can appear here. And if the 5 takes the sixth place, 6 can appear here. But now 5 cannot take the 7th place. Okay? Because there is nothing beyond it. So for 6, there will not be any position left. Right? So if I want a sequence 56, for number 5, I have 1, 2, 3, 4, 5, and 6 options. Right? So for the number 5, we have 6 options. Okay. Considering the position of 6 is fixed, that is after 5. So once you decide the position, so for number 5, we have 5 options. For number 5, we have 6 options. 6 doesn't have any options. 6 has the number after 5 only. Now, once I decide 5, okay, once I decide the position of 5, automatically 2 positions are gone. Okay, automatically 2 positions are gone. So now for the remaining places, we have 7p5. For remaining 5 places can be filled by 7p5bs. Okay. So total number of options what I get over here is 5 into 7p5. That is the number of ways I can generate a number which has a sequence 56. Now the same argument I can give for 65. So for 65 also, I have 5 into 7p5 options. And that's why my total cardinality of S bar turns out to be 2 times, it was 6 here, I'm sorry. It has 6 options. Okay. So for 5, there is a correction here. There is a 6 over here. So 6 over here. So I have the value 2 times of 6 into 7p5. Right. The cardinality of S will be cardinality of U minus cardinality of S bar. That is 9p7 minus 2 times of 6 into 7p5. Right. So that is how one can handle the question by using a permutation in this. Okay. Now under the permutation, I have been emphasizing in the first problem that I'm right now talking about the straight line permutation. So obviously there has to be a circular permutation. The circular permutation comes into picture when you are talking about the arrangement of the people around the table, or you are talking about the necklace problem. Okay. So that is where you are going to talk about circular arrangement. So suppose the number of circular arrangement of R permutations of a set of n elements. R permutation means you are having n elements. From that you are choosing R element and you are arranging them. Okay. So the arrangement of R objects out of N objects around the circle. Okay, it is given by NPR divided by R. Okay, so it is N factorial divided by R into N minus R factorial. So in particular, if I'm talking about circular permutations of all N elements, it turns out to be N minus 1 factorial. Okay. Let us take an example over here. 10 people, including 2, who do not wish to sit next to one another, are to be seated at the round table. How many circular seating arrangements are there? Okay. So here what we are going to do is, first we'll find out. So there are 10 people, all of them have to sit around the table, right? So first of all, since we have 10 people can be arranged table in 10 minus 1, that is 9 factorial. Just give me a minute, please. Okay, so 10 people can be made sit around the table in 10 minus 1, that is 9 factorial. That will be the cardinality of my universal set. Now, when I find the cardinality of universal set, obviously I'm going to solve this problem by using a complementary event. So in order to understand the complementary event, let us write down our set S1. So S1 denotes the total number of round table arrangement where P1 and P2 are to be together in the form of. So here I'm going to take two arrangements. Now there is a possibility. One second. I'll just try to wait. Just give me a. Okay, so this is what I'm trying to tell you. Now, there's a possibility that when you are making a round table arrangement, let us call those people as P1 and P2, those who don't wish to sit together. So there is a possibility that P1 is here and P2 is sitting on the right of P1. Okay, and here is another possibility that I have a round table arrangement where P1 is sitting where P1 is here, where P1 is sitting, and P2 is sitting to the left of P1, right? So these are two possibilities, and that based on that only I have decided my P1 and P2. So let us say S is the total number of round table arrangement where P1 and P2 are sitting together, but P2 is sitting on the right of P1. Okay. So now the total number of arrangements. So now what we can do is we can treat P1 and P2 as one person. Okay. So now I have in all 8 people to arrange because P1 position is fixed. And with respect to P1, P2 ka position is already decided that P2 will be sitting on the right of P1. Right. So we have to arrange only 9 people as P2 position depends on P2. So 9 people can be arranged around the circle in 9 minus 1, that is 8 factorial ways. Okay. So this is an arrangement where P2 is sitting on the right of P1. Now similarly, let us say S2 is a set similar to S1 only, the sitting arrangement. But now P2 is sitting on the left of P1. So now once P1 ka position is decided, P2 is going to take the place on the left of P1. So for P2, there is no choice. I just have to decide the arrangement for P1. Okay. So P1 plus the remaining 8. That means I have 9 people. So 9 people can be arranged once again in a 9 minus 1, that is 8 factorial ways. Right. So now P1 and P2 are the people those who are actually having a problem and who don't wish to sit together. So the number of arrangements where P1 and P2 are not together, it is a complementary set of S1 union S2, right? So that is cardinality of U minus cardinality of sum of the cardinalities of S1 and S2. So that turns out to be 9 factorial minus 2 into 8 factorial, which on simplification gives you answer 7 into 8 factorial. So that is how we arrange the round table question, sitting arrangement around the table. Okay. Now there is a classic question which is called a necklace problem. Okay. So what is a necklace problem? Necklace problem is, suppose you have different colorful beads, and by using those beads you have to form a necklace, right? So now when you are forming a necklace, how many the arrangement of a different beads, okay, the different arrangement of those different color beads will give you a different necklace. So this is slightly tricky question. Let us understand what is the trick over here. So it says you have to count the number of necklaces. The importance is, what you need to understand is you are counting the number of necklaces. Okay, you're not counting the number of arrangement of the beads. That is a difference between the earlier problem and this problem. What you are doing is you are counting the number of distinct necklaces. Those can be formed by using 20 beads, each of different color. Okay, so now there are 20 beads only, and you are arranging 20 beads around the circle. So total number of arrangement will be 20 minus 1, that is 19 factorial beads. Okay, so that is the number of arrangements of the beads. It is not the number of necklaces, because when you, now here I have taken one small example. Suppose you look at this particular necklace, okay, or maybe you can look at this particular necklace. So here in the counterclockwise direction, I have green first, followed by blue, followed by red. But now if I take a look of the same necklace in the mirror, okay, I see a different arrangement in the anti-clockwise direction, that is red followed by blue followed by green. So these two arrangements, they are different. So permutation wise, this arrangement is different from this arrangement, but as a necklace, they are one and the same thing. So if I consider this, my total number of necklaces actually turns out to be half of this value. That is 19 factorial divided by 2. Okay. So that means the necklaces can be turned over without changing the arrangement. Hence, the total number of distinct necklaces is 19 factorial upon 2. Okay. So that is, so under the, inside the round table, you have, inside the circular arrangement, popular questions are round table arrangement for the dinner or for a, maybe for a meeting or something. And second is a necklace question, what one should see. And the third topic which comes under permutation is permutation of a repeated symbols. Okay, so suppose you are forming a word by using a collection wherein you have repeated letters. So that is called a permutation of a multiset. Now to understand a multiset, to understand the permutation of a multiset, one should know what is a multiset. So multiset is a set, okay, except the elements are not distinct. The elements are not going to be distinct here. Okay, so here is an example. Suppose consider M, which contains 3A, 2B, 2C, and 1D. So this becomes a good example of a multiset. The only thing is, for our convenience, we'll write down this as 3 times A, comma 2 times B, comma 2 times C, comma 1 times D. So this 3 to 1 basically denote the multiplicity of the element of the set. Now we're talking about permutation of a multiset. So suppose S is a multiset with the elements of K different types. Okay, you have a set where you have K different types of element with a finite repetitions N1, N2, and N3. Now, when it is a question of multiset, there are two kinds of multiset. One which has the finite repetition, like a number of objects. The first of all, cardinality of S is finite, and the number of repetitions in a set is finite. Okay, so basically a finite multiset, and you have an infinite multiset. We'll see one example of infinite multiset later on. So S is a multiset with the objects of K different type with the finite repetition N1, N2, and Nk. So first object is repeated N1 times, second object is repeated N2 times, and the kth object is repeated Nk times. Then cardinality of S is Cardinality of S will be n, which is n1 plus n2 plus nk. And the number of permutations of S. Number of permutation is number of arrangements of all the objects of the S. It is given by n factorial divided by n1 factorial, n2 factorial, nk factorial. Okay. Now here is a very classic example of a river named Mississippi. Named Mississippi. So number of permutations of the letters in the word Mississippi. So first count how many letters. First of all, let us write down the multiply. I have written the answer here, so don't look at the answer for a moment. So I need to work out the number of permutations here. So what will I do in that case? First, I will write down the multi-set corresponding to the word. So as I can see, there are only 4 alphabets which appear here: M, S, I, and P. So M appears once, S appears 4 times, so it is 4 times S. I appears 2 times and P appears 2 times. So the multi-set of this particular word is given as an S over here. The cardinality of S is 11. So the number of words, the number of permutations of letters over here, which can be formed by using this letters from the word Mississippi, is 11 factorial divided by the product of the factorials of the repetition. So it is 1 factorial into 4 factorial into 4 factorial into 2 factorial. Okay. So here I'm considering the permutation of all symbols which appears in the letter Mississippi. Now this is another example. Like I am not interested in taking a permutation of all the elements of the S, but I am only interested in taking some part of S and permuting that. Okay. So I have a set S. So consider a multi-set S, which is given over here. And so as you can see here, it has 9 objects. So 2 times of 3 times of A, 2 times of B, and 4 times of C. So there are 9 objects here with the repetition. The question is, find the 8 permutations of S. What do I mean by 8 permutation? Choose 8 elements of this. Okay. And find how many ways it can be permuted. Now, if you look at the theorem which is given above, it talks about permutations of all the symbols. Okay. And we are not choosing R and we are permuting R. That kind of option is not there. You have to, the formula works for entire set. So task 1, when you get such kind of question, that you have a multi-set and now you have to select some object and permute, you need to understand how many possibilities I will have. So let us find all the possibilities for selecting R permutation. R permutation ka you need to work out your S. So now I have 3 A's, 2 B's, and 4 C's. So in all I have 9 elements. So if I'm going for a 9 element combination, one possibility is from 3 A's, I'm just trying to fit them in the frame. From 3 A's, you choose 2 A. Then you choose both the B's and then you choose 4C. So as you can see here, 2 plus 2 plus 4. So I am done with one subset which contains 8 elements of S. Okay. Then the second possibility is you choose all the 3 A's. So if you are choosing all the 3 A's, you can cut down on 1 B. So you take 1 times of B and 4 times of C. So this becomes your second subset of S, which contains 8 elements. Similarly, you choose all the 3 A's, but now you choose 2B and then you will have to choose 3C. Then you have the third subset of S, which contains 8 elements. Now, other than these 3, there is no possibility of making the subset of S, which has 8 elements. You can try on your own. These are the only possibilities in which you can form a subset of S, which has exactly 8 elements. Okay. Now, total number of 8 permutations of S. It is total number of permutations on P1, total number of permutations of P2, and the total number of permutations of P3. So total number of final permutations will be permutations of P1 plus permutations of P2 plus permutation of P3 by using the addition principle. So let us find out. That is what I have mentioned here. Total number of 8 permutations of S is number of permutations of P1, number of permutations on the set P2, and number of permutations of set P3. Okay. So let us go ahead with P1. Let us talk about, I don't have that down. So if I'm talking about permutations of P1, if I use the formula which is given here, which says it is cardinality of set divided by product of the factorial of cardinality of S divided by factorial of the partition. Okay, so in that case, if I'm talking about cardinality of P1, it is, there are 8 elements here. So the answer of cardinality of P1 will be 8 factorial divided by 2 factorial into 2 factorial into 4 factorial, which is mentioned here. Okay. Similarly, if I'm talking about cardinality of P2, it is not fitting in the same screen. So if I'm talking about cardinality of P2, so total number of element in P2 is 8. So it is 8 factorial divided by 3 factorial into 1 factorial into 4 factorial. And cardinality of P3 will be 8. Total is 8. So 8 factorial divided by 3 factorial into 2 factorial into 3 factorial. That turns out to be this. Okay. So this is cardinality of P1, cardinality of P2, cardinality of P3. Their sum will give me total number of 8 permutations over S. Okay. After permutation, the next topic is combination. Combination is selection. You can treat selection as a synonym for combination. Right? So if I have to select R objects out of n identical objects, then that is called the combination. Okay, and the combination ka formula, what we have seen from our 11th or 12th standard, it is NCR, which is n factorial divided by R factorial into n minus R factorial. Now, if I keep 1 by R factorial aside, whatever is left inside this bracket is basically NCR. So that gives me a relation between NCR and NPR. NCR is equal to NPR upon R factorial. Okay. Now here is one very nice application of this in geometry. Suppose you have 25 points. Now you can choose as many points as you want. I just found a number 25. So there are 25 points in the plane, so that no 3 points are collinear. Okay. I'm highlighting the condition that I'm not taking any set which has collinear points. No 3 points are collinear. Okay. There are no 3 points which are collinear. Then how many straight lines can be drawn and how many triangles can be drawn? Now, the simple rule for the straight line is there is exactly one straight line passing through 2 points. Okay, and the simple rule for the triangle is to draw a triangle, I just need 3 points, 3 non-collinear points. Okay, so I have already mentioned that the points are not collinear, right? So first of all, let us talk about straight line. So to draw the straight line, out of 25 points, I have to choose 2 points and I have to draw the straight line. Okay, so drawing a straight line comes down to selecting 2 points out of 25 points. So number of straight line is number of ways of selecting 2 points out of 25 points, which can be selected in 25C2 way. Don't look at this number. This can be calculated on your own. Right? Similarly, if I have to draw a triangle, so there is a simple rule that every 3 points determines a unique triangle. Okay, so number of triangles. To draw a triangle, I need to select 3 points. So total number of triangle is total number of ways of selecting 3 points out of 25 points, which is 25C. Okay. Now coming to the problem number 2. So how many 8-letter words can be constructed by using 26 alphabets if each word contains 3 or 4 or 5 vowels? Okay. So we know that in 26 alphabets, there are 5 vowels, A, E, I, O, U. And with removing vowels, you have 21 consonants. Okay. So the set of alphabet actually can be divided into 2 distinct subsets. One subset is set of vowels and another subset is set of consonants. So from the problem statement, it is clear that repetition is allowed because nowhere they said I want a word with the distinct alphabet. So repetition is allowed in this case. Now, since repetition is allowed, we will divide this condition that it contains 3 vowels or 4 vowels or 5 vowels into what should I say? Into 3 cases. So let us say S1 is a set of words. Okay, it's a 8-letter words. So I have made a partition of 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. So I have made a provision to write down my 8-letter words over here. So let S1 be the set which contains 3 vowels and 5 consonants. Okay, so I need 3 places. So out of these 8 boxes, I need to compulsory fill 3 boxes with vowel. Okay, maybe I can show that over here. There is no hard and fast rule that it has to appear like this. So I have 1, 2, 3, 4, 5, 6. And maybe I'll take this as an example. So let us decide that I fill the first position by using a vowel. Now, how many vowels I have? I have 5 vowels. So for the first place, I have 5 options. Let us decide that I'm filling the second place also with the help of vowel. Okay. So for the second place also, I have 5 options. Let us say I decide to fill the fourth place by using vowel. So I have 5 options, right? Now the remaining places have to be filled with the help of consonants. So for the second place, I have 21 options. Then for this place, again 21. For this place, again 21. For this place, again 21. And for this place, I have 21 options, right? So I can see that for 3 places, I have 5 options. And for 5 places, I have 21 options. So if I'm looking at cardinality of S1, okay. So again, as you can see here, it's a tuple, no? It is actually an 8 tuple. So out of 8, in the 8 tuple, 3 coordinates have 5 options. So by multiplication theorem, the cardinality of S1 will be 5 cube, because for 3 places I have 5 options. And for remaining 5 places, I have 21 options. So 21 raised to 5. So that is how we calculate the cardinality of S1 by executing the multiplication principle. And that is what has been stated over here in the solution. So first select 3 places out of 8. Now that can be done in 8C3 ways. Now I did not bother to show the number of selection of the place. I am considering that over here. And then for the 3 places, select 3 vowels, and for the remaining 5 boxes, you have to fill the consonant, right? So you have 21 choices per box. So cardinality of S1 is, you are right. Understand the way you are doing the task. Task 1, choose 3 places. So 3 places out of 8 places can be chosen in 8C3 ways, right? So selection is done. Now you have to fill up the values. So for those 3 places, you have 5. For each place, you have 5 options. So for 3 places, in all, you have 5 cube options. For remaining 5 places, you have 21 options. So total number of choices will be 21 raised to 5. So cardinality of S1 is 8C3 into 5 cube into 21 raised to 5. Now going to S2, wherein I have 4 vowels. Okay. So first of all, task 1, choose 4 places out of 8. So that can be done in 8C4 ways. In those 4 places, you are going to put vowels. So for those 4 places, each place you have 5 options. So in all for 4 places, you have 5 raised to 4 options. And then remaining, you have consonants. So 21 raised to 4. Similarly, if you have 5 vowels, selection of 5 places, 8C5. For vowels, you have 5 raised to 5 options. For consonant, you have 21. Total number of words will be cardinality of S1 plus cardinality of S2 plus cardinality of S3. Addition principle comes into picture here. And this is the answer what you get. Okay. This is the value of 8C3, 8C4, 8C5. Okay. So this is combination of a set S. Now let us talk about combination of multi-set. And this is the beginning wherein you are going to, after this, you will go ahead with the binomial theorem and multinomial theorem. And the problems what you get in this category are slightly different and they are interesting. So S is a multi-set. Multi-set. multi-set once again means it's a set with the repeated elements. Then the R combination of S is a selection of R objects of S, which is a subset of size R of S. Okay. Basically, what is a combination? Like you have been given a set and you are just taking out some element of S, right? There is no arrangement here. You're just taking out some element. So if you take a set S, so if you take a set S, so if you have a set S, and from that you are selecting a part of it. Obviously, whatever part you are taking, this becomes a subset of S. Okay, so that is what is mentioned in this line. That if you are just choosing R combination of S, basically you are forming a subset of size or of R of S. Okay. The important part is when my value of R is equal to N, which is a cardinal, N is nothing but a cardinality of S. So you have N objects and you are selecting N objects, right? So what will be the N combinations of S? That will be set S only. Okay. And if R is a multi-set with a finite repetition, then any R combination of S is a R subset of S, which I have already spoken about. We'll consider a multi-set S with K types of object and with infinite repetition. The point what I want to highlight over here is I'm going to consider a multi-set where the number of repetitions are infinite. And this is where you get some good questions. Okay, so here is a result which says that let S be a multi-set with K types of object, each with infinite repetition. So let us say S is equal to infinity times A1, infinity times A2, infinity times AK. There is nothing like infinity, but what I'm trying to say over here is the number of choices available for A1. It is not finite. Like you demand for A1 and number of A1s are available. Okay. So this is a representation of an infinite multiset. So what it says is the number of R combinations of S. Okay, suppose from this set you want to choose R combinations of S. The number of R combinations of S is given by the formula R, that means how many objects you want to select, plus K, how many types of objects you have, minus 1 CR. Okay, I hope you understand. R is how many objects you need. Let us say the value you want 5 objects, and the value of R is 5. K is the type of objects which are available. Okay, so the value of R combinations of a multiset with an infinite repetition, it is R plus K minus 1 CR. Now this is very easy to understand. Like if you just see this, okay, so R plus K minus 1 CR is same as R plus K minus 1 CK minus 1. That is the property of combination. Based on this, we have a very good question here. This is called a bakery problem. Okay, so a bakery boasts 8 varieties of donuts. If a box of donut contains 1 dozen means 12 donuts. How many different options are there for the boxes? Now the boxes are decided by how many combinations you have, possible combinations you have. Okay, now what I'm doing here is I'm just denoting DI. My DI will stand for one particular variety of donut. And now since there are 8 varieties of donut, my I will vary from 1 to 8. Now bakery doesn't have a restriction on number of donuts. Okay, they never said for D1 I have only 10 donuts or for D2 type I have only 15 donuts. So I assume that if I demand for more donuts of one particular type, they will provide me. So here the multi-set is going to be infinity times D1, comma infinity times D2, comma infinity. So this is an infinite multi-set. Okay, I have 8 types of donuts. So the value of K in this question is 8. Okay, and I want 12 donuts. Okay, I'm going to select 12 donuts because a box can be formed by using 12 donuts. So in order to make a box, we must select 12 objects of X, which has 8 types of elements. So by using the formula which is given there, the number of boxes is equal to 12 combinations of X, okay, which has 8 types of objects. So the answer is 12 plus 8 minus 1 C12. That turns out to be 19. These many choices for boxes will be available to us. Okay. Now here is another good question which can be discussed over here. What is the number of non-decreasing sequences of length r whose terms are taken from 1 to k? Okay, so now I'm not talking about the increasing sequence. I said non-decreasing. Now non-decreasing is actually not an antonym for the increasing. Non-decreasing means it could be increasing or it could be flat in between. Okay, it could go up or it can be flat. So maybe you can have a sequence like 1, 2, 3, 3, 4, 5 and so on. So as you can see, 3 is repeated. So that's absolutely fine. So first of all, I have to form a sequence of length r, means it should have r numbers in the non-decreasing order. Okay, and the numbers have to be taken from 1 to k. So my multi-set is going to be all the elements from 1 to k with an infinite repetition. Right? Now, how do I form a non-decreasing sequence? The logic is simple. First, you choose r elements, and then you arrange them in a non-decreasing order. Okay. So what is important over here is selection. So you have k options. From that, you are choosing r options, and it's a multi-set. So your number of selections is going to be r plus k minus 1 CR. Now the question arises is, why am I not considering the permutation here? Because there is only one way of arranging them, because my order is fixed. Okay. So total number of selection is r plus k minus 1 times 1. So these many non-decreasing sequence I am going to get. Okay. This is something which is very interesting question. Finding the number of non-negative integer solutions for a linear equation. Okay. So how many non-negative integer solutions will be there for the linear equation in k variable? So here I have a linear equation in x1, x2, xk. I have k parameter, k variable, and this is equated to r. So there is a theorem. Actually, it is a part of an earlier theorem which I have stated. So number of non-negative integer solution for x1 plus x2 plus xk equal to r is given by r plus k minus 1 CR. Okay, basically you are choosing r options from a multi-set which has k variety. So the number of selection is given by r plus k minus 1 CR. Okay. Now, what you need to understand is this is applicable when you talk about the non-negative integer solution. Fine. So if you insert, that means my x1 is greater than or equal to 0, my x2 is greater than or equal to 0, and xk is greater than or equal to 0, and all of them are integer. Now, if you replace any of the condition of xk by something else, okay, then you will have to do some adjustment, which we'll see in the problem. So here we go ahead. The number of non-negative integer solution, just a demonstration of the formula. Solution of x1 plus x2 plus x3 plus x4 equal to 5. So here the value of k is 4 and the value of r is 5. So my answer is 5 plus 4 minus 1 C5, that is 8. Okay, so this problem is a straightforward application of formula. There is no experimentation done over here. Look at the second problem, and that is what I meant by saying if you insert some more condition, then there will be some alteration. So find the number of positive integral solution. Okay, positive integral solution means I'm talking about the solution which is greater than 0, and the first integer which is greater than 0 is 1. So the condition what I have is x1, x2, x3, x4 all are greater than or equal to 1. And my formula works only when my variables are greater than or equal to 0. So I will need a change of variable here. We'll see that. To find the integral solution of x1, integral solution of x1 plus x2 plus x3 plus x4 equal to 0, with the condition that each of them is bigger than or equal to 1, we'll do the change of variable. So now we'll take y1, y2, y3, y4 as xi minus 1. Okay, so since x1 is bigger than 1, y1, which is x1 minus 1, will be bigger than 0. Similarly, y2 will be bigger than 0, y3 will be greater than or equal to 0, and y4 will be bigger than or equal to 0. So this equation, x1 plus x2 plus x3 plus x4 equal to 10. If I write down this in terms of y1, okay, so you just have to make y1 and then you consider y1 plus y2 plus y3 plus y4. So that will turn out to be this, and then use this particular result. So I will just do it that here instead of. So your current condition is x1 plus x2 plus x3 plus x4 equal to 10, right? And you want to convert this in terms of y1, y2. But what is y1? y1 is x1 minus 1. Consider y1 plus y2 plus y3 plus y4. Okay. So y1 is x1 minus 1. y2 is x2 minus 1. y3 is x3 minus 1. And y4 is x4 minus 1. So if I add them up, I get x1 plus x2 plus x3 plus x4 minus 4. Now, but this value is 10. Okay. So my equation of x1, x2, x3, x4 equal to 10 turns out to be y1 plus y2 plus y3 plus y4 equal to 6. Okay, and that's what I have done here. So it's kind of change of variable. So this turns out to be y1 plus y2 plus y3 plus y4 equal to 6, where all yi's are greater than 0. So total number of solution for the original equation is same as total number of non-negative integer solution for the new equations in y, which is precisely 6 plus 4 minus 1 C6, which is 84. 9 C6, forget the number 84, that can be calculated. Okay, and this is one exercise I have left for you. You can just do the change of parameter. And if you want more problem, the reference is Gruwaldi, Richard Gruwaldi. Now going to the binomial theorem. Okay, we have been using binomial theorem from our school, and it says that if n is a positive integer, the binomial theorem actually can be worked out when n is not an integer, but combinatorics paper, it is we are fine with positive integer. So, I have a variable x and y, and n is a positive integer. So x plus y raised to n is given by x raised to n plus nc1, x raised to n minus 1y, and so on. Okay. In a summation form, it can be written as k going from 0 to n, nck, x raised to n minus k, y raised to k. What we need to do is work out some basic results of binomial theorem, and that is what I expect can be a part of your paper. So when x is equal to 1, y is equal to 1, just put x and y equal to 1. Okay. So your binomial statement, which is this one, will change to nc0 plus nc1 plus nc2 plus ncn equal to 2 raised to n. 1 plus 1 raised to n, so 2 raised to n. Here you put x equal to 1, y equal to minus 1. So the left hand side will be 0. And on the right hand side, you will have nc0 minus nc1 plus nc2 minus nc3. And finally, minus 1 raised to n ncn, that is equal to 0. Okay, now this has been discussed further. Second part has its own application. But I forgot to, I just inserted Pascal formula here. So I will come back to second one after 2 minutes. There's a Pascal formula which talk about NCK ka relation. NCK is equal to n minus 1 CK plus n minus 1 CK minus 1. It's a very good identity to remember. It helps you to prove, give the proof of binomial theorem. Okay, again, in case you have done Leibniz rule. Okay, the proof of Leibniz rule, which talk about the nth order derivative of u into v. That proof is the k plus 1 case is possible only by the Pascal formula. Okay. Now some of the identity here, that k times nck is n times n minus 1 ck minus 1. Okay. And the thing what I was referring is this. By using first and second. Now what I'm saying first one is this. First one is this. Okay, and this is the second one. So by using the first and second one, the value of nc0 plus nc2 plus nc4 and equal to nc1 plus nc3 plus nc5, this will turn out to be 2 raised to n minus 1. Right? Now, in binomial theorem, if I take y equal to 1, so if I take, maybe I will take x equal to 1 and y equal to x. Okay. So my binomial theorem formula turns out to be 1 plus x raised to n equal to nc summation of nck x raised to k. Now, since k is x is a variable here, we can differentiate both the side with respect to x. So we get n 1 plus x raised to n minus 1 is equal to summation of k times nck x raised to k minus 1. At this point, you put x equal to 1, you have this new result, which I have listed as 6. And finally, by using a Pascal's identity, you can attend the 7th result. Okay. I'm not getting into the proof of this. I have 3 more pages to discuss. So these are the results what one should know. What is a multinomial theorem? So binomial theorem gives me an expansion of x plus y raised to n. Okay. But what if instead of 2 variable, I have n variable? So summation, the n power of x1 plus x2 plus xk raised to n. It is given by summation of n choose n1, n2, nk. So what is this notation? Just give me a moment. I will discuss this after 2 minutes. This is basically a combination. From n, you are selecting n1, n2, and nk. Okay. Notation will be discussed in 2 minutes. Into x1 raised to n1, into x2 raised to n2, into xk raised to nk. Where the summation extends over the non-negative integer solutions of n1 plus n2 plus nk equal to n. Forget this non-linear, non-negative integer solution. Basically, summation, the condition is, the summation is over the condition that the sum of n1 plus n2 plus nk should add up to n, which is the power over here. Now, coming back to this notation, n choose n1. Remember the term what I'm using here. N choose n1, n2, nk. It stands for n factorial divided by n1 factorial into n2 factorial into nk factorial. I have done a mistake here. Okay, I think this will work. Okay, it is nk factorial. Okay, and we have already seen this somewhere. Okay, now you just figure out where did we see this. If you recall your example of Mississippi, the number of arrangements of the letters of the words Mississippi, we have seen this particular number there. So this is a combination that is selecting n1 plus n2 plus nk out of. By the way, this number which I just listed here, this number which I just listed here, I forgot to mention, it is a multinomial coefficient. As nck is a binomial coefficient, this is multinomial coefficient. Now, how do I use this? This is used to find the coefficient of, now there are 2 examples what I have taken here. It is used to find the coefficient of a particular power of a product of powers of xi. So here is a very simple question. Find the coefficient of x1 raised to 5, x3 square, x2, x4 raised to 2, x5 in the expansion of x1 plus x2 plus x3 plus x4 plus x5 raised to 10. So first of all, the value of, first you see here, the sum of the powers should be equal to the total power here. So it is 5 plus 2 plus 2 plus 1, that is 10. Okay. So my binomial theorem is applicable. So my multinomial theorem is applicable. And by multinomial theorem, the coefficient of this is the multinomial coefficient, which is n choose n1, n2, n3, n4, and n5. Okay. What is n1? N1 is a power of x1. So power of, first of all, n is the total power, that is 10. Okay. N1, it's a power of x1. The power of x1 over here is 5. N2 is a power of x2. x2 is not seen here, so the power is 0. N3, power of x3. N4, power of x4. N5 is the power of x5. So put the value here. It is n factorial divided by n1 factorial, n2 factorial, n3, n4, n5 factorial. So that covers your first example. Now, the second type, what one should consider is when you have multiples of, you have an expression where the multiples of x1, x2, x3 are not equal to 1. Okay. So in that case, if someone asks me what is the coefficient of x, power of x1 into power of x2 into power of x3, I shouldn't be forgetting the coefficient of x1, x2, x3 here. So first of all, just add them up. So 3 plus 1, 4 plus 2, 6. So n is sum of n1, n2, and n3. That's fine. Okay, so by multinomial theorem, the coefficient of this particular, the multinomial coefficient of this is going to be 6, 2, 3, 1, 2 into the coefficient of x1 raised to 3 into coefficient of x2 raised to 1 into coefficient of x3 squared because of this. Okay, substitute, simplify, we will have the answer. Okay. Now this is something which I was not able to include. Up to binomial theorem, everything gets over here. But then there are some more questions which one should try. This is another good question, though it is not a part of your syllabus. I have included JAM syllabus. I have included this over here. This is called principle of inclusion exclusion. Principle of inclusion exclusion can be treated as a generalization of principle of addition. So basically, what it says, this is something what you must have done in your 11th or 12th standard. The formula is something which we have already seen under permutation combination in 12th standard. Okay, so here you have set A, here you have set B. Okay, so this is your set A, this is your set B. Now if I have to calculate cardinality of A union B, then it is cardinality of A plus cardinality of B minus cardinality of common cardinal. That is principle of inclusion exclusion, right? So that's what I had said. So if A and B are two sets, necessarily not disjoint, because if they are disjoint, it becomes the addition principle. Okay, because the cardinality of intersection will turn out to be 0. So cardinality of A union B is A plus B. Cardinality of A plus cardinality of B minus the cardinality of A intersection B. For 3 sets, it is summation of cardinality of single set minus summation of cardinality of intersection of 2 sets plus cardinality of intersection of sets. Now, this is something which is used popularly in the problems which are given in Ruvaldi. In general, the statement appears like this. So, summation of cardinality of single sets minus the intersection of 2 sets plus the intersection of 3 sets minus the intersection of 4 sets. Finally, minus 1 raised to n plus 1 intersection of all n sets. Okay, this is provided you are proving the theorem in the class right now. Let us not look at this particular. Here is one very nice example you should see. It's a very good use of floor function. Now, what is a floor function? So, floor function says if you have a number. Okay, so let us say, I'll just give you an example. So if you have a number which is a decimal or a perfect number, so you will scale it, you will bring it down. So the floor value of 1.1 will be equal to 1. The floor value of 1.9 will be equal to 1. If I'm talking about floor value of minus 1.1, it will turn out to be minus 2. So it will pull it down. Now going over here, the question is find the integers between 1 to 1000, both inclusive. That means number 1 is also there. So you are considering a set like 1, 2, 3, 4, 5 up to 1000, which are not divisible by 5, 6, and 8. Okay. So first of all, let us count. Let us take our U as a set, which is a universal set. All the integers between 1 to 1000. The answer is 3000. Cardinality is 1000. Suppose A is a set of all the integers between 1 to 1000, both inclusive, such that n is divisible by 5. So number of elements which are divisible by 5 between 1 to 1000. It is 1000 divided by 5, the floor function, that is 200. Now I have to find the numbers which are divisible by 6. So it is 1000 divided by 6, which is floor value of 166.66, that is 166. Similarly, for A3, numbers divisible by 8, 1000 divided by 8, the answer is 125. Now, when it comes to number divisible by 5 and 6, a number will be divisible by 5 and 6 if it is divisible by their LCM. Okay, so the cardinality of A1 intersection A2, it is 1000 divided by 30, floor value is 30. A2 intersection A3, that is a number divisible by 6 and 8. So it is divisible by LCM of 6 and 8. Answer is 41. A1 intersection A3, a number divisible by 5 and 8. So it is 1000 divided by LCM of 5 and 8. The answer is 25. And finally, A1 intersection A2 intersection A3, it is a number divisible by LCM of 5, 6, 8. That is 1000 divided by 120. That turns out to be 8. So the numbers which are divisible by 5, 6 and 5 or 6 or 8, that is cardinality of E1 union A2 union A3. I apply the principle of inclusion exclusion. So this summation of cardinalities of EI minus the intersection of 2 plus the intersection of 2. That is the formula. I'm not putting any value and simplifying at this particular point. My question is not to find the numbers which are divisible. My question is to find the numbers which are not divisible by 5 or 5 and 6 and 8. So it's a complementary event. So it is a complement of A1 union A2 union A3, which is precisely A bar intersection A1 bar intersection A2 bar intersection A3 bar. So it is U minus the union, okay, which will turn out to be 1000 minus this particular value. Okay, I have done a mistake over here. I just need to make the correction here. This number needs to be rectified. So I'm just cancelling it for a time, right? I have done a mistake while writing this. Okay, this needs to be corrected, or maybe I have done a mistake in the question. Just give me a 1 to 1000. No? Yeah, I have done a mistake in writing the answer. Okay, so this is not a correct answer. I have done a calculation mistake. Okay, now after principle of inclusion exclusion, I will stop here for the session. The topics which you are expected to, so let us conclude the session properly. So topics are covered: 4 basic principles, permutation combination of set and a multi-set. Permutation means you are seeing the straight line arrangement, circular arrangement, and permutation of a multi-set. Combination of a set and a multi-set. Under binomial theorem, then the results of binomial theorem and multinomial theorem and its application. Another topic what I have just touched and go, that is principle of inclusion exclusion. There are very good questions on principle of inclusion exclusion. The question which I did not cover is derangement, and that is what one should at least try. It's a very simple topic. It is hardly 1 or 1.5 page in zoology. One should check. Then permutations on n numbers, that is Sn, the properties of Sn, that we have already done in our graduate course. So just go through Sn. Combination of multi-set on a finite repetition, that requires little extra time, so I have not covered there. Like you take, let us say you have A1 of N1 type, A2 of A1 element which is repeated N1 times, A2 elements repeated N2 times. So finite repetitions I have not done, but you have a questions on this also in zoology. And pigeonhole principle, weak and strong form. That I did not cover here because that was not going with the theme of the session. Okay, now with this, I will just stop my session. Now, wait a minute, let me just
Okay. Thank you, Dipali ma'am, for this nice session with a good collection of problems and explanations.
One minute, I'm not able to stop my screen.
Yeah. Yes. So, dear participants, now it is your time to ask any queries or share your feedback. Feel free to share your feedback.
Hello.
Yes, Harsh.
Yeah, no, I don't have any queries. I just wanted to thank ma'am because normally professors don't take the session so easily and from scratch. They assume that we know many things, but you took it very fluently and explained everything quite well. So thank you.
Thank you.
Thank you, Harsh. Could you introduce yourself?
Thank you, ma'am. I just want to say a big thank you and for giving us a clear and helpful lecture on permutations and combinations. The way you explained everything and made it easy to understand really helped us a lot. And also special thanks to Professor Vinod.
Okay, thank you, Namrata.
Hello, ma'am. Ma'am,
Yes, sir.
Archana, ma'am, have completed my BSc. Ma'am, I really enjoyed your session. And ma'am, as permutation is a new subject, you have explained us a lot of new concept compared to what we had learned in 12th, 11th, and 12th. So more than this, what else should we refer and from which book or something which should we refer for questions as well as for concepts for JAM level?
The best book for this is Introductory Combinatorics by Richard Rualdi, and it is very nicely written. I do have a copy here. I'll just show you the copy. Just give me a minute. So this is the book I'm talking about. Introductory Combinatorics by Richard Rualdi. I'll share the soft copy also. I'll share the link.
Okay.
But this is the very nicely written book. We had the course under Mumbai University at our college, and I taught this course 2 times. And this is very friendly book for undergraduate student. It is the best book. Okay, I deliberately took the questions from here and the collection of the problems in Rualdi. And if you are going for principle of inclusion exclusion, there is a book, I think, I don't remember the topic, I think it is Discrete Structures by Kenneth Rosen. That is another good book. But I like Richard Rualdi. It is good for undergraduate students.
Sure, ma'am. Thank you so much. Really enjoyed this session, ma'am. And thank you, Vinod sir, for organizing this session.
Okay, thank you, Archana.
Good morning, ma'am. Good morning, sir. My name is Varada. I have also completed my BSc, and like right now I'm preparing for JAM. So I also enjoyed this session throughout, ma'am. Like I was also very bit unsure about how to approach this topic because it was not there in the previous years. But the way you explained the concepts, it actually built my confidence as well to approach different sort of problems. So thank you so much, ma'am. Ma'am, I have a doubt. Like, in which year was this topic there at the last time this topic was there for JAM?
I think it is newly added. That's what sir said. Even I'm preparing my students for JAM at our college, and this is newly added topic. So,
Okay, so
I just refer to the syllabus of Mumbai University, which was on discrete structures, discrete mathematics. So we had, let us say, some 3 or 4 chapters. I think from chapter number 2 to chapter number 6 of Rualdi was the syllabus for Mumbai University. Chapter number 2 is pigeonhole principle till it went till principle of inclusion exclusion. That is chapter 2 to 6. That is what I expect to come for this particular JAM examination, including your SN. On SN, you have very nice question, permutations over n symbol. So you can study SN, then study the properties of AN and the dihedral group DN. So the questions can be asked even on that part. That is what I expect.
okay, ma'am. Okay. Thank you so much, ma'am, for this session. And thank you, Vinod sir, for organizing this class.
Thank you, Varada.
Hello, hello, ma'am. Myself Sneha,
Yes.
and I have completed my masters from 𝐼SET. Now I am preparing for CSIR, NEET, and GATE. But I never had any course in combinatorics after 11th, so it was very informative session. I really enjoyed it, and it has lots of concepts more than 11th and 10th class. So it was very nice, and thank you for that. I just wanted to learn this new topic. I never, because during my jam time, I didn't study that topic. So it was very good session. Thank you, ma'am.
Yeah, thank you. It is actually a nice topic, and for those who wish to do their research in combinatorics, this becomes the plinth for their research. I think foundation for the research is basically for introductory combinatorics. Those who are interested in doing research in combinatorics, they should take up this particular course.
Thank you. Thank you, Sneha.
Good afternoon, ma'am.
Yeah, good afternoon.
Ma'am, this is a really fantastic session. I think this is a different session from other session
Thank you.
because this
I
is
hope
a
you
new added
enjoyed and
topic.
understood. Yeah, yeah. I just hope you understood the topic. It doesn't require any background to start, and it can be completed in one go. Maximum part can be completed in one go.
Yes, ma'am.
Do well
Thank you,
in
ma'am.
your exam. Do well in your exam, Nadia. What is the motive here?
Thank you.
Yeah.
Okay, thank you, Akash. Any others?
Hi, ma'am. Hi, sir. I'm Shabiba. I'm a BSc third year student. The lecture was very helpful. I understood the concept with the use of that examples you have given for every concept. I didn't started preparing for this topic, but I think I got a strong base for this topic. Thank you, ma'am, and thank you, sir.
Okay, thank you, Shabiba. Any others? If any of you would like to share a feedback or ask something, please do make it now.
Hello, ma'am.
Otherwise, yeah.
Yes.
Hello, ma'am.
Yes. Yes. Yes.
A very good afternoon to ma'am.
Thank you.
I am BSc first year math student, ma'am.
Okay.
Myself, 𝐿𝐿 Sharma.
What is your doubt?
Madam, my doubt is what is the best book for permutations to prepare for IIT JAM, ma'am?
For this, I have already said it is Introductory Combinatorics by Richard Pruvaldi. I think someone has mentioned that in the chat. That's the book what I have referred for preparing this particular topic. And you will find problems also in the exercise, and the answers are given. The final answer is given in the end. So if you are interested, so maybe for JAM, whatever I have done should be good enough. But then remaining, if you want to read extra, it is Introductory Combinatorics by Richard Pruvaldi.
Okay, thank you, ma'am.
Okay, thank you.
Thank you, sir.
Yeah. So thank you, Dipali ma'am, for being with Math Aspirants and for helping our members. I request your continued support in our journey.
Yeah, it will always be there. And the only thing is that sometimes this topic take little longer, so it is not possible on a frequent basis. But this is something of my interest also. I had taught this course at my institute at least 2 times. 2 times only I got an opportunity to teach. And the book was written very nicely. So there was a good reference to start.
So please do share the PDF that you have prepared that we can share with the students.
Yeah, there could be some corrections here and there because I just noticed it when I did not get time to actually type it. It is only my handwritten thing. So there is not much correction, but if there is a correction and if students want, they can just get back to me on the Maths Aspirant feedback.
Okay.
Mostly all the problems are from Richard Pruvaldi. So if they want to verify the answer, I have the 4th edition here, but on the Google you will find the latest edition. So mostly all the problems are from Richard Pruvaldi. It is basically chapter number 3 to 6.
So as this topic was not there for it was there in some years, but recently this is not in the syllabus. So people are actually have a worry about how the questions will be there like that. Yeah, okay. And also, this time IIT Bombay is organizing, while in the last year when IIT Madras was organized the JAM examination, The exam was too tough and the cutoff are very low. So people really having lot of worries about this time examination.
It will be fine. Students will have to only study properly. Whatever
Yeah.
efforts you are taking, even if they attend the lectures and give the practice test, they should be able to clear. Sincere efforts, students will be able to clear.
Yeah. The main part is from their hard work and their dedication will.
Yes, self-study actually makes a lot of difference.
And also we used to provide many such resources that are helping also. But yeah, let us hope that our participants will be able to clear the examination with good ranks.
Hello.
Well,
Yeah.
yes, Harsh.
I'm sorry to take more of your time, ma'am. Just because you mentioned self study right now, I just have one very big doubt that is going on. I'm in SYBSc mathematics right now, but since FYBSc, what happens is when I'm trying to do a proof on my own, or when I'm trying to understand, if one statement बीच में अगर कुछ नहीं समझा, or if it does not click, then it takes up a lot of time that I thought कि in 1 hour I will complete these many things, but just because of that one statement or one thing, one not clicking of a concept, a lot of time goes by. So if I want to understand proofs well, so is there some, there might not be a technique, but is there a procedure that I can follow?
Use the reference book mentioned in your syllabus. Nothing comes outside the reference book. Suppose you are reading a proof for real analysis, and if the book mention is Robert Bartle, you should read Robert Bartle. You'll find the proof over there. If I'm saying you are referring to you are doing group theory, refer to Gallian. If the Gallian is mentioned in your syllabus, that's the best way of getting the proof. Or go back and ask your teacher. Your teacher will definitely help you out.
Yeah.
That is, and if you are asking me from JAM point of view, you will mostly have applications. Okay, so you may not struggle with the proof. You give importance to the theorem. You should know the theorem statement, and you should be able to use the theorem statement to solve the problems. As I did today, I did
Yeah,
not
yeah,
put
not jam point of view. Jam to only numerical answers and all.
yes. So develop a habit of
Yeah.
reading reference books, which I mentioned in your syllabus book. That will help you to understand your paper better.
Okay, got it, ma'am. Thank you.
So once again, thank you, Miss Dipali, for being with us. Let us wind up the session here.
Yes. Thank you for the opportunity given. I actually, initially it is little difficult to start, but once I start preparing the topic, I really like the way I get an opportunity to prepare my notes once again. I get an opportunity to look at the subject in a different way. So when as a student you study the paper, and as a teacher when you teach different kind of group, your preparation is different. That helps me to explore the paper also. Nicely. Thank you for the opportunity also, sir.
So please
Hello,
do.
sir.
Yeah. Yes, Jida.
Hello, ma'am. Hello, sir. Hello, ma'am. And thanks a lot. Actually, these topics are in our syllabus here. In first semester, in the paper Introduction to Number Theory and Group Theory. There is a small unit. In Unit 1, they are putting these topics. And so it's very helpful here. So
Okay.
thanks a lot to both of you. For,
Okay, thank you, Jida.
thank you, sir and ma'am. Bye.
Yeah, right. So Dipali ma'am, after making the corrections, if possible, please do share the PDF. I will share it with the students along with the recording of the session.
Yeah, I'll just go through them one more time. I found one correction when I was giving the lecture. That was the last line. I think I lost the track of the problem towards the end. So there was one correction, and I did not provide many details, but the notes are self-explanatory because this will be accompanied with the video, right? So there should not be having a problem. I will share immediately. I just need to read them one more time.
Okay. Okay, thank you. Okay,
Thank you,
let us
sir.
Yeah. Let us wind up this session here. Thank you, everyone.
Thank you, sir. Bye. Thank you, students.